This is CPR for exam 3, question 7. Let us first start off with the equation for a force coming on a current carrying wire in a magnetic field. This equation is the permeability of free space multiplied by I dl cross the magnetic field H. We can use this equation to find the force on a moving charge in a magnetic field. Let us first look at a single electron in a portion of a circuit with charge Q. The definition of current is the rate at which charge passes by a point in a circuit. We know that given no external forces, that the charge will move at a velocity u. Given all that, we can say that the current induced by charge Q is equal to Q dt, the time. This essentially gives us the definition of current we just talked about. We can also say that the velocity is just the rate at which the charge is being displaced, dl over dt. We can rearrange this equation and say that dl is equal to u dt. Now that we found the current and velocity for a given charge, we can plug in what we found back into the equation we know for a current carrying wire. We can substitute I as q over dt and dl as u dt. We can cross out dt, and now we have the force on a moving charge Q is equal to the permeability of free space multiplied by the charge and velocity cross the magnetic field intensity H. We can also combine the permeability of free space and the magnetic field intensity to equal B, the magnetic flux density field. We can use this equation now to solve this problem. There's an aluminum ion that is moving with a constant speed u and enters a region where the magnetic flux density goes into the page. Given that and the right-hand rule, we know that given the direction of the speed and direction of magnetic flux density, that the force that the charge feels is in the negative y direction. Because the force is perpendicular to the velocity, we know that the charge will experience a centripetal acceleration and eventually exit the region, but at a lower y region, which in this case is 9 times 10 to the negative 2 meters below the starting point. Since there's a centripetal acceleration, we can say that the force that the charge experienced is the mass times the centripetal acceleration, which is the velocity squared over the radius, 9 times 10 to the negative 2 meters over 2. We can now simplify the equation and move all non-velocity variables to the right, and we get that the velocity is equal to the charge times the magnetic flux density times the radius divided by the mass. We can now plug in our values given from the problem, and we get that the speed is equal to 10 to the 4 meters per second.